Okay, so welcome everyone to the first module of the eTool training session for consultants. It's just a basic intro to LCA, the basics, what is lifecycle assessment, what does this thing mean, why do we need it, why is it useful, and get into a bit more of the technical side of things, look at some of the more technical aspects of LCA later on. But yeah, to start with, we're just going to talk about who is eTool, what are we about, why we created, a bit of LCA basics, what is LCA, reporting sort of standards that we can report to, and then get on to functional units, which is a really important aspect of LCA and something that I think is often forgotten about, or maybe not considered as seriously as you'd hope. It really does have a huge impact on the results and the performance of the building, which we will see as the training progresses and as people start modelling their own buildings and completing their own LCAs. So to start with, eTool software, we were created, Alex and Richard, our directors over in Australia, both engineers, one in mining and one in renewables at the time. About 6 years ago, got asked to do this kind of carbon footprinting assessment of this residential building called EarthCare. At the time, they'd never really heard of life cycle carbon assessment. They just knew that they needed to calculate everything. They didn't have a huge amount of experience, I suppose. They didn't know that maybe thermal performance was important, or how important it was compared to transport of materials or production of those materials. So they really just went back to complete first principles and ran the calculations in a spreadsheet. Sort of realized what they'd done is this thing called life cycle assessment, and sort of went on from there, because in Australia at the time there's very little going on in the sustainability industry in terms of buildings. There's a little bit done in thermal performance, but not a huge amount, and yeah, certainly no tool for calculating life cycle carbon assessments of buildings. So yeah, they built this tool, and it was on a spreadsheet originally. This particular project did win multiple awards. They did get it to zero carbon, and yeah, fantastic project, and really what spawned eTool, and it's grown dramatically since then. We've moved from a spreadsheet tool that we very quickly realized wasn't up to the job to this web-based platform, getting involved in all sorts of different types of projects, lots of residential at the beginning, now lots of commercial, lots of larger projects, and we've also seen the LCA industry as itself sort of grow alongside that over the years, which I'll get onto a little bit later. But first up, what's the problem? How big's the need? Why do we worry about carbon? And the main reason is climate change. So here's a map of the carbon impacts on a per person per year basis. And so this is what we're worried about at the end of the day. The fact that a lot of the developing countries are really high in terms of per person per year carbon figures. Looking at 20 tons per person per year in Australia, America, Canada, maybe 15 around Europe, which is unsustainable at the moment. And the global average is sitting around about 7 tons per person per year. And as the developing countries become more developed, if they continue the same sort of pattern, then we're going to see them all rise up to 20 tons, 30 tons per person per year, which isn't sustainable. What is sustainable? The IPCC have suggested we want to be looking at around about 1 ton per person per year. The planet does have an ability to absorb a certain amount of carbon at the moment, but it's not 20 tons per person per year. It's around about 1 ton per person per year. And yeah, so big problem, lots of work to do, and hopefully we're on the right path and getting there eventually. So what about buildings within that? So worldwide, 30 to 40% of all primary energy is used in buildings. That's from the UN Environmental Programme 2007. Not just them that sort of claim these figures. It is widely reported around about 30 to 40% area commercial and residential, 39% of carbon dioxide emissions in the US. US Information Administration, nearly half of all CO2 emissions in 2008 came from the building sector. So yeah, buildings are a massive problem, and if we're not going to get to zero carbon or close to zero carbon buildings, we're really not going to be doing enough to combat climate change. And so that's what it's all about. That's sort of taking a step back from the nitty-gritty day-to-day of what we do as consultants, and say, okay, this is where we're at, and this is where we're trying to get to: 1 ton per person per year or less. Obviously, the population is increasing a little bit, so maybe we want to be thinking about even less than 1 ton per person per year. But yeah, that's the ultimate end goal. That's what we're trying to achieve, basically. There are fringe benefits, I suppose, when you look at carbon, especially in life cycle terms. You do tend to see improvement in financial performance as well. So what you're looking at here, this is an automated graph produced from eTool, from the software. You've got an average kind of residential building, and you've got an improved design that we've sort of modeled with sustainable features, technologies incorporated into the building. Obviously, increasing initial capital to pay for some of these features, but over the life cycle of these buildings, more than made up for. You're only looking at 22 years there, and you're seeing an ultimate saving. You keep following that progression onwards for the life cycle of a building, which may be 100 years, and you're going to see really very, very significant savings. So eTool vision. eTool, we love solving problems. Global warming is a problem, and that's something that we're trying to address, basically. And our goals are to provide LCA software free of charge to maximize availability to all, and to enable dramatic reduction in global CO2 emissions. What we noticed was, there was consultants out there who do run their own spreadsheets and can get involved in the really large projects, and it's sort of viable to do so and get some good savings, but they're still missing out on a massive chunk of the building industry. Certainly in America and Australia, a huge amount of buildings going up by the small builders, the medium-sized sort of businesses who don't have the sort of funds to bring in big fancy consultants. So what we've done is we have developed this business model where the software is free to use for non-commercial gain. That means that anybody on the planet can jump into the software, start to run their models, and start to understand how to make their buildings better, which was really important for us at the time. Obviously, we do have to make money somehow, and I'll get onto our business sort of model later. But essentially, software is available for anyone to use, to jump on and look at the buildings. What we ask is that when people are selling those results or making money themselves out of those results, or using them for things like environmental rating schemes, then we certify the jobs, and there's a fee with that. But the actual access to the software is open use. We want to propagate the use of eTool as quickly and effectively as possible for education, training, and marketing. Lots of webinars that we all run, a lot of engagement, hopefully, with the building industry and consultants and developers and architects, and always keen to get involved, lend our expertise, lend our hands, whether it's for an hour or so for a webinar, or for more detailed training such as this. We want to utilise our profits to further fund other actions to enhance the quality of life for humanity in a sustainable fashion. Mainly, our funds, all the money that comes into our eTool, gets put back into eTool, gets put back into making the tool more functional, building the software's capabilities, and propagating LCA, I suppose, into the industry is where we're putting all of our resources at the moment. We do have signed up to 1% for the planet. That's where we send 1% of all our revenue rather than our profits, 1% of all of our revenue goes to a charity cause that we pick each year. Last year it was, I think, with the Black Cockatoo Research sort of facility in Australia. And we also want to practice business in a financially sustainable and ethical manner while providing a high-quality work environment for all employees and subcontractors. You know, we want LCA to be engaged by everyone. We want an open door, basically, for anyone who's interested in life cycle assessment, in improving their buildings. You know, to feel that they can come and approach us, you know, and get some initial answers, whether it's just, you know, a quick chat on the phone or whether it's more detailed software provision and training, etc. So, yeah, doors are always open to people who are interested. So LCA, the basics. This is the life cycle of steel. You know, one of the core ingredients, I guess, in lots of buildings today. And there's impacts throughout every single process that the steel's got. So initially you have to extract that iron ore from the ground, and there's impacts associated with that. The equipment that you need, the people that you need to come and extract this metal from the ground has some impacts. Then you've got to process and refine that metal that you found in the ground and try and produce some steel out of it that's useful. After that steel will get made into your actual steel product. So in this case, it might be a steel girder for the bridge. The bridge will be around for a while, and in the case of steel, you will also maybe need to replace certain elements. You'll certainly need to coat it in sort of anti-rust paint, and there'll be impacts associated with that to maintain the steel over its life cycle. You know, you might get some damage or storm damage or something like this where you have to actually replace some of the girders within the bridge itself as well. So there is impacts associated with maintaining this product over its life cycle as well. And then eventually one day this bridge will be knocked down. It will come to the end of its life. Nothing does last forever at the moment, and yeah, maybe in 100 years' time or so, we will need to build a bigger bridge in its place, or it'll just have rusted and become unsafe. So it gets knocked down, and there's end of life impacts associated with this steel, whether it goes to recycling or whether it goes to landfill. And in the case of a steel bridge, probably the vast majority of it's going to go to recycling. There's still impacts associated with the recycling plant, collecting all the steel, melting it down, recycling, etc. Then hopefully it gets fed back into this system and then probably head straight to the refining plant there. And there's also transport involved in all of those. So, from resource extraction to the refinery, you have to transport the steel, and you have to transport it throughout all of these life cycle stages. And that might be long distance over land, it might be some shorter distance over the trains or boats, whatever it might be. There's transport impacts associated with all of these stages. So the definition of life cycle assessment. Life cycle assessment is a process to evaluate the environmental burdens associated with a product, process, or activity. Identifying and quantifying energy and materials used and waste released to the environment, to assess the impact of those energy and materials used and releases to the environment, and to identify and evaluate opportunities to effect environmental improvements. The assessment includes the entire life cycle of the product, process, or activity, encompassing extracting and processing of raw materials, manufacturing, transport, distribution, use and reuse, maintenance, recycling, and final disposal. So, a bit of a wordy definition, I guess, but some key things that jump out at us there is that it's an evaluation tool. It's looking at environmental burdens. LCA is strictly interested in environmental impacts. So, whether it's CO2, acidification, things that happen to the environment. Life cycle cost, something slightly different, which we will maybe get onto in later stages of the training. But environmental burdens is what we're talking about. So we're quantifying energy, materials, and waste, and we're assessing impacts. And then most important, I suppose, element of this definition here is that we're identifying improvements. There's really no point in doing all of this work to evaluate, to quantify, to assess, if you're not going to change your behavior, improve the design, improve the building. And one of the most important elements, and something that we have built the tool to make accessible, I suppose, to help people really understand where their impacts are and where they can be improved. Prioritize those sort of strategies, think about the recommendations, and this is where we really want to spend most of our time when we're running an LCA. We've got a lot of detailed background data and a lot of work that's gone into building the tool to help all these early stages happen very quickly and effectively, which allows us as consultants to really focus on the improvements, on making a building better. So what's an LCA involved? Well, you always need to assess your goal and your scope. Think about your system boundaries. What's included in the LCA, what are you not going to include in the LCA. Think about assumptions and limitations, impact categories. Are you looking at CO2? Are you looking at water or eutrophication? Maybe a mixture of them all. And then crucially, your functional unit. What's the purpose of this product? What's it trying to achieve? And what are the impacts in terms of what it is achieving, which I'll get onto later. You've got your life cycle inventory, so that's your kind of raw data that's feeding into this assessment. The database of materials impacts, of trade staff impacts, of equipment impacts, of energy impacts. You've got a raw database in the background there that you will be using when you're building up your model. Then you've got your actual impact assessment, quantifying the amount of materials that you're using, taking that inventory data and multiplying it by the quantity that you've got. So you've got meters cubed of concrete. You've got an inventory database that tells you, you've got 1 ton of carbon per meter cubed of concrete, and apply that to how many meters cubed you've got in your model, and you're beginning to build up your life cycle assessment. Then you've got to interpret the results, understand where are the hot points, what are the big impacts here that we want to be focusing our attention on. And then there's often a critical review at some stage as well. So somebody coming in externally and checking your results, which is what our certification is about as well. So they're the key components of an LCA built up in the industry. Every LCA that is completed should be pretty clear on what all these elements are. It must be transparent enough to be repeatable, accurate enough to be reliable. But we didn't just make all that up. There's LCA standards, and they all started a while ago, I suppose, with ISO 14040 and 14044. And these are standards for a product or a service. So maybe it's a chair or a table or something, a specific product. And there's a standard associated with doing an LCA on this product. If you follow this standard, then it can be compared. You compare 2 chairs like for like that have been different manufacturers and different LCAs applied. Then the sort of building industry was like, maybe we should have some of these for specific building products. So what we developed was environmental product declarations, and they follow the ISO 14025 standard, and then eventually within the building level 15804 standard. So that's when a manufacturer of concrete or of steel beams or of plasterboard, there's specific standards associated with completing an EPD and making it comparable in the building industry. So when you're looking at EPDs and building products, you want to be looking whether they've followed their standard and that they can be comparable. Then at the next level we go to EN15978, and this is talking about LCAs of whole buildings, and thinking about the calculation methodologies, data sets, what's appropriate to be used in an LCA of a whole building. And again, any building with an LCA that's done to 15978 will be comparable, which is a sort of fair way to have an understanding of these things. There are various platforms, EcoEBD, with libraries and databases of EBDs of products. Bream have their own one. Germany has their own one, quite a significant one. France also has one. So keep an eye out on those if you're looking for specific construction product EBDs. So example of a system boundary. So I guess this is quite important. In this case, we've got a concrete system boundary, and what we've included within this specific LCA is plant waste disposal, the plant operations for the concrete, handling and storage of the aggregates, and handling and storage of the cement. We haven't included transporting the cement from its manufacture plant to this concrete plant. We haven't included the aggregate production. We haven't included electricity and fuels that have gone into this plant. We've just included the operations, the disposal, the handling and storage. In this case, we could extend the boundary to include some of those elements, or all of those elements. We could extend it even further. So, you might want to take, okay, well, what about all the embodied energy that went into the cement plant up here? There's concrete that have gone into that. There's manufacture of the actual building itself. Then there's people that had to go to that cement plant to put it together. They traveled there in cars. There's embodied carbon in their cars. There's embodied carbon in the houses that they live in. What about the people that built those houses and how they transport the people? You could go on and on forever ad infinitum, to the beginning of the Industrial Revolution, maybe even further if you wanted to. But what you see is that you have diminishing returns. So, the wider your scope is, the much harder it is to both calculate and understand, but also the smaller the impacts are having on the LCA. The closer you are to the source of the impacts, in this case, the plant operations, they're where the bulk of the impacts are going to be, and everything else is adding another level of detail, but that level of detail is always a little bit smaller. That makes sense. So we don't take LCAs of the whole Industrial Revolution because it wouldn't be that much more accurate than an LCA of the usual sort of system boundary that we're looking at, if that makes sense. Here's the EN15978 boundary. So in this case, we've got A1 to A3. So this is the initial product stage. So building, your plasterboard or your concrete, whatever it might be. You've got raw materials extraction is included in this case. You've got transport of those raw materials to the manufacturing plant. You've got the actual manufacturing, A3 there. Then you've got construction stage, so you've got to transport them from the plant to this building site where they get built. Then you've got construction installation, so you've got maybe a concrete pump to pump the concrete into the floor, the wall, or whatever it might be in installation. Then you've got use stage, so concrete might excrete some carbon or sequester some carbon over the course of its life cycle. It might need maintaining, repairing, replacing, refurbishment. We've split out all those impacts under EN15978. In a building, there's also operational energy and operational water required to run the thing, and that's covered in these stages B6. Just B6 or minor 1 there. Then you've got end of life. What happens when this building gets demolished? There's some impacts associated with that demolition and deconstruction. Your explosives to blow up the thing, or the wrecking ball, whatever it might be. There's some impacts associated with that. You've got to transport all those materials somewhere once you've knocked them all down, separated them. There's some processing, whether it's in recycling or plant or the landfill disposal plant, and there's some disposal impacts. Timber in particular can have very large disposal impacts. A lot of carbon sequestered inside timber that can get released if it's not disposed of well. So that's the initial boundary of EN15978. Then under EN15978 there's an optional benefits and loads beyond the building life cycle, category D. And in that is, these are elements that are sort of outside the initial physical realm of the building, and it's benefits for providing more materials into the economy, or providing more energy into the energy grid. These are sort of benefits to another building or to another project, or being outside of the actual physical boundary of your actual building, but they are benefits that should be attributed in some way to your building. You put the steel in the building, then you sent the steel to another building. Let's give some credit for that. That makes sense. Things that are out of scope, but we also include our transport of construction labour. So we do include the impacts of transport, site staff going from their home basically to the site to put the building together. We don't include the impacts of the embodied impacts of the cars that they went in, or the embodied impacts of the houses that they live in, or the people that built those houses, etc., etc., etc. These all you'll find when you look at transport of labour, actually, when you're modelling, that this is quite a small impact. And if you started to look beyond that element and into an even wider scope, you'd see such tiny fractions of an increase in your overall impacts that it's really not worth bothering with, and get to the cut-off rules a bit more later. Then we have operational energy used within the building, so things like your appliances. In the UK, you call that unregulated emissions. I'm doing EN15978, only looking at the regulated stuff, your HVAC, hot water and lighting. Appliances we do include in an eTool assessment, but it's an optional extra under EN15978. So cut-off rules, speaking a little bit there about how do you know when to stop? How do you know when to say enough is enough with this LCA modelling? And they enable practical application of LCA. You don't want to be doing this assessment for years and years and years. When you've got 99.9% of the accuracy in the first couple of hours of your modelling. So what we say is all mass flows greater than 1% of the total do need to be included. All energy flows greater than 1% of the total need to be included. The sum of anything that you've neglected should not be greater than 5% of the total. And environmental relevance, everything should be greater than 1% of the impact category. So if it's looking at CO2 and you've got a building with 1,000 tons of CO2, and you're looking at this small aspect of it, maybe a waste paper bin or something, what the impacts of this waste paper bin, and they're only a kilogram of CO2. That was it's not adding significantly to the accuracy of this particular building. Its environmental relevance is much less than 1%, and it can be discounted or not included. I guess maybe you might have noticed by then there was a sort of paradox there, in that you have to know the final result of the LCA, so you can show that the emission of a certain process is insignificant for the overall results. In the case of the paper bin there, we've already had to calculate it so that we can understand that it's less than 1%. And then, you might as well just chuck it in anyway, because you've already done the work. And that's what we find with LCAs, and every LCA that we do, we do a little test, find something in the building that we think is irrelevant, but you never know, it might pop up as something significant. Run it as a test, see that it's far less than 1%, probably more like 0.01%, and then we know that we've probably got a reasonable model here, and we've accounted for anything as far as reasonably possible, and that's the ultimate goal that we're trying to achieve. It might be a good point there just to bring up this templates in an office. So what we're looking at here is two figures actually. This is percentage of total impacts, and this is percentage of embodied only impacts, so just the materials that have gone into the building and the train staff, the assembly. So yeah, you see that this concrete floor slab, 3% of the total impacts in terms of CO2, and 23% of the total embodied impacts. So it jumps up when you take out that operational energy and you don't include it. And yeah, we'll see some pretty significant things that we want to include, and we also want to make sure are reasonably accurate. Have we got the right quantity, the right floor area, the right assumptions here in terms of the thickness of the slab. These are things that we do want to sort of make sure that we're being accurate on, because they are significant elements of this building. In this case, foundations again, carpets. These are significant, and as you run more and more LCAs, you get a good understanding of what the important parts are and what are not so important. And we do go down here into detail, things like your cabinetry, your doors, water tanks, shower units, all these embodied impacts that are starting to become really quite small and insignificant. Yeah, down all the way there to 0.01 of embodied, or 0.003. You have to add up quite a lot there to get to your 5%. Yeah, so yeah, quick example there, I suppose, of what cut-off rules are and how they're applied. And with a bit of experience, the first few LCAs, you start to very quickly see what's important and what's maybe not so important. So operational guidance for lifecycle assessment studies, yeah, apparent paradox, just talked about there. And yeah, it's just about a pragmatic approach to continue modelling eventualities until confidence is gained that the cut-off criteria has been safely met. In that case, I was very confident that I'd met the cut-off criteria, as including many impacts that were much less than 1% of the yeah, not necessary, but I added them in any case because I've got them available. Might as well, it doesn't take too long. So data quality, next up. LCA is only as good as the input data, and this is two elements basically. You've got the user collected inventory data, so that's your materials take up, how much concrete's used in your building, how much steel, how many meters squared of plasterboard, how many liters of paint, etc., etc., etc. Then you've got the background data, all the environmental flows to produce these materials. So at the moment, the eTool users are only influencing this collected inventory. You're quantifying the amount of materials that are used, and then you're using our LCI databases. Where we have a couple now. We have the impact database, and we have the EN15978 LCI database, and they're locked in. There's no way to change those, and they get applied to what you've quantified in your materials takeoff. Data quality needs to be of temporal relevance. It should be up to date. 2016 now. All of our data gets updated annually. I think VRE data about to be updated again. Yeah, LCI database regularly updated. Does it have geographical relevance? Is it appropriate for your area? It needs to be precise, it needs to be complete, technological, it needs to be consistent and reproducible. So allocation rules. When two products flow from one process, how do we allocate the environmental burdens of that process to the two products? Yeah, the best way to explain that is the example that we've got coming up. So there's a couple of ways to tackle it: mass or energy. What we like to do is economic allocation, which seems the most fair way to allocate the impacts. So in this case, you've got a sheep. Now, sheep have very high CO2 impacts. They burp a lot, they fart a lot, they produce methane, which is quite a serious greenhouse gas, 20 more times potent than CO2. And but this sheep is producing, it's producing two products. It's producing lamb, which is sold, and it's producing wool, which also has economic value. And what we do is proportion the impacts by what the economic value of this sheep is. So in the case of lamb versus wool, they'll probably the sheep's making more money out of the lamb than the wool. Sometimes, occasionally, you do get waste wool from sheep. But yeah, the wool generally has a smaller economic value anyway than the lamb. So we attribute the impacts proportionally as well. Smaller impacts to the wool and more significant impacts to the lamb that's being produced. And likewise with steel, you've got for the core production of steel, the primary purpose is to produce steel products from the steel mill, but you do also get this almost waste product called blast furnace slag, and blast furnace slag is useful in aggregates and roads and things like this, but it has very little economic value and therefore very little impacts as well. Compared to the steel, which is the primary focus of this steel mill is to produce the steel. So the vast majority of the impacts go into the steel. It might be that we find more alternatives to steel and it becomes a less useful product. And for some reason, blast furnace slag is becoming a more useful product. Maybe we're running out of aggregates or something. It's hypothetical. And those impacts change, and we start to attribute more to the blast furnace slag. But at the moment, mainly steel mills are there to produce steel, and we attribute the vast majority of the impacts to the steel. Likewise, in coal power plants, the primary focus is to produce electricity. One of their byproducts is fly ash, and there's almost zero value to that fly ash. They would pay you to take it away in some instances. So zero economic value and therefore almost zero impacts associated, allocated to that fly ash product. Again, if fly ash, if we start putting fly ash in all of our concrete and we start to get a small economic value with it compared to this electricity, then we would see that the impacts that we allocate to that fly ash increase ever so slightly. So yeah, something to be aware of is allocating the impacts from these processes that produce maybe two materials or two elements. So end of life allocation, closed loop. The primary purpose, I suppose, of recycling in the closed loop scenario, we've really got to be careful when we're doing this LCA analysis that we don't double count where the impacts get allocated. So yeah, that's a sort of rough idea of what's happening, but it's probably easier if I jump into the example to show you what's going on there. So in the case of this is aluminium. So if you look at the top one there, you're looking at it's got 0% content and 100% of it's recovered at the end of its life. So 100% primary aluminium used in this case, quite significant impacts at product stage. Transport those, construct them, put them on site, leave the building for a while, and then at the end of the building's life, it's aluminium, all of it's getting recycled, all of it's being fed back into the aluminium economy, and you receive some significant credit for that because yeah, all this primary content aluminium is going back into the economy, and some fairly small impacts there. When you compare that to 100% content, you say, okay, you've got quite small impacts there at the product stage because you're using all this recycled aluminium, so that's great. But if you don't recover it at the end of its life, you get a significant increase in your impacts there because yeah, you're not receiving this benefit for recycling at the end of its life. Significant impacts there, and what that adds up to is the total increase compared to the original ones. It's really really about not double counting and about, in this case, it rewards end of life recovery a lot higher than initial content of recycled. Then we go to 100% content, 100% recycled. Yeah, as we'd expect, very low impacts at the start and very low impacts at the end, but we don't get that significant credit that we got at the start because we've already claimed benefit at the product stage. That we've got 100% content here. We can't claim that benefit twice. You can't recycle. Yeah, so we have to not double count these impacts, and we see slightly counterintuitively that we have the same impacts as the first case scenario. But yeah, what we've done is avoid that need for double counting in the case of these recycling impacts. It's not the only way to calculate recycling, and lots of people might be discussing alternatives and how they might be better. But under EN15978, this is the way that it's done. So impact categories. At eTool, our primary focus has always been global warming, but we do have the ability to calculate a number of other impact, environmental impact indicators, acidification, ozone, marine aquatic ecotoxicity, terrestrial ecotoxicity, abiotic resource depletion, non-renewables, minerals, human toxicity, ionization, radiation, land transformation, respiratory effects, smog, aquatic ecotoxicity, eutrophication, and water depletion. And it's quite interesting that what you'll find is actually there are quite a lot of these impact indicators that are directly affected by CO2 as well. So, or have fossil fuels as their most significant element, and so reducing global warming, reducing the burning of fossil fuels, also reduces the impacts to some of these other elements. Smog, obviously, land transmission, resource depletion, fairly obvious direct reductions there if you're reducing your CO2. And there's also indirect reductions in a lot of these other ones. When you reduce the CO2, you do often reduce ozone and terrestrial ecotoxicity indirectly as well. Water and ionizing radiation, I suppose, are outliers there. They're quite standalone impact elements that, not at all really affected by CO2 or fossil fuel burning. So functional units, crucial element to LCA, and easiest just to take an example again. In this case, we've got the two coffee machines. The one on the left there is very low in embodied carbon, 22 kilograms of CO2, that probably is. Cost, very low, $100, and not much embodied energy that's gone into this this coffee machine. Compare that to this heavy-duty commercial style one. Significantly higher cost, 40 times the impact of this one in terms of cost. Significantly higher initial CO2, lots of steel, lots of manufacturing gone into that. In this case, 10 times what this one is. And significantly more embodied energy as well, energy required to build this thing. So this one, significantly more impacts compared to this one. But that's not really a fair comparison. We're not comparing apples to apples in that case, are we? What we want to be looking at and thinking about is what's the purpose of this coffee machine? What is it there to do? It's there to make cups of coffee, and we want to think about, how many cups of coffee can they make? Okay, well, the one on the left can make 730 cups of coffee, and the one on the right in its life is going to make 100 times that. So this one's producing far more cups of coffee than this one. That's the primary purpose of these machines. And what we want to be thinking about is impacts per cup of coffee. And when you break that down into cost impacts per cup of coffee, you see that option 2 is much cheaper. Embodied carbon impacts, again, option 2, much cheaper, much less embodied carbon associated with that on a per cup of coffee basis, and much less embodied energy. So actually what we see is in this case option 2, always the best option. If you've got a need over your life for 730,000 cups of coffee, or 73,000 cups of coffee, this one is significantly lower in impacts than the one on the left here. Interesting there that you do want to think about the life of this cup of coffee machine as well. If you did only need a single coffee machine for a single event somewhere, then you only wanted 100 odd cups of coffee, then maybe you do want to go for a lightweight option. Obviously though, it's pretty rare that happens. Somebody will always find a use for a coffee machine. So everyone should be thinking about the impacts per cup of coffee, basically, is what that's trying to say. And the same goes for buildings. So what's the purpose of a residential building? The purpose is to provide space for somebody to live. So we want to be thinking about impacts per occupant per year. This building has 10 tons of CO2 per occupant per year. Commercial office space, well, the purpose of that is to provide space for people to work. So the more space you can provide for people to work, the better. So we think about impacts per meter squared per year. You might want to also put in occupants per year. In that case, the purpose of the office is really to provide a space for somebody to work in. So you might be thinking about impacts per occupant in that instance as well. Hotel, you want impact per bed per year. It's the purpose of a hotel. A bridge, impacts per crossing or impact per standard axle crossing. With a standard car, higher impacts for larger trucks, etc. So standard axle, a truck might have 10 standard axles, whatever it might be. So impacts per standard axle is a fair comparison there in terms of functional unit for a bridge or a road. And so that sort of brings us back to that 1 ton per person per year ultimate goal when we're thinking about all these elements that we have in our society and what their impacts are per occupant. This as a human, I live in my house, I have 10 tons, I go to my office, I have half a ton, I stay in a hotel for 10 nights a year. If 1 ton per bed night, you might put in that case. I cross this road to get to work, and every time I cross it, I have 0.1 tons. You really build up this picture of why we're at 20 tons per person per year, and how to get back down to a sustainable level of half a ton or less per person per year. So summary there. Key goal of an LCA should be identify how to increase the functionality and reduce the impacts of a product or service. How do you make more cups of coffee, more people in the building, or as well as reducing the impacts of the materials required to produce that building. In construction, there are often a lot more gains to be made by increasing functionality, service life and service provision, increasing the life cycle of the building, how long it's going to sit there, increasing the number of people that can use the building, rather than reducing the materials impacts that tend to have slightly less of an effect on the overall life cycle than your functional unit. Double the people in a building, you half the impacts without even touching the material side of things. Okay, that's the end of that module. I will sign off from there.